Hi everybody. In this section we're going to learn to find the average value of a function. The problem is, if you look at a function over an interval, it has infinitely many values. And we don't know how to average infinitely many values. The familiar formula average equals the sum of the numbers divided by the number of numbers doesn't work. And before we go on to find out what we are going to do, let me just review this notation with the Greek sigma letter here. That's the summation notation that we've seen before. Also, dividing by n is the same thing as multiplying by 1 over n. So I'm going to write this way to look a little more familiar. And then the sum as I goes from 1 to n of a sub I means a sub 1 plus a sub 2, so on and so forth, until you get up to a sub n. So what I typed there really is just our familiar old average formula. Anyway, this doesn't work if we have infinitely many numbers to average, but if those numbers are function values, it turns out the definite integral can help us. So let's suppose we want to get the average of all the values of the function f of x on the interval from a to b. We're going to start out by leveraging that average formula that we do know, and we're going to do this by picking a finite number of function values. So let's say we're going to pick n function values on the interval from a to b. And we'll average those, and that's going to be an approximation of the average of all of them. So I've shown here that I've picked out a number of x values. Now, I wanted to be generic with n, so what I did was I showed that we had x1 star, x2 star, and I went ahead and picked dots up to x5 star. And then I left a gap here, so you can put in like a dot, 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 meaning etc., up to the generic x value, which I called x sub I star. And then, again, I left a gap so as not to predetermine how many x values there are, except that that last one is x sub n. So we have n of them. Now what we're averaging isn't the x values, of course, it's the function values. So for example, here we have f of x sub 1 star. Here, for example, we have f of x sub 3 star. In the middle there we have the generic f of x sub I star. And like I said, we're going to use these to approximate the average of all the function values by simply adding them up and dividing by n. The notation for the average of a function value, this is pretty standard, is f sub ave, and I've used the squiggly approximation symbol there because what I've written here is not the actual average of all of them, it's just an approximation. By the way, my equation editor is refusing to put a star in there, so let's change that little dot to a star. Now then, it seems reasonable to define the actual average of all the function values to be the limit as n goes to infinity, because as n gets bigger and bigger and bigger, we're taking more and more and more of those function values. So it should be that the thing we want will be the limit of the normal average here. Now, if this is seeming kind of familiar to you, if it's reminding you maybe of what we did when we first developed the definite integral, you're right. It is very similar to that. In fact, let's take a quick look back at what we did there. I think that'll help us understand what's going on here. Back in section 5.1, we were trying to find the exact area under a curve and above the x-axis. And the way we got a handle on that problem was to approximate the area by picking n x values, using the function value at each of those x values, and then using that function value as the height of a rectangle. And the total area of our rectangles was our approximation of the exact area under the curve. And the way that calculation looked was area is approximately equal to the sum of the f of x sub I stars times delta x. And then we defined the exact area to be the limit as n went to infinity of that sum. Then in section 5.2, we introduced this new notation and terminology. We called the limit of that sum the definite integral from a to b. And then in section 5.3, we got the very powerful fundamental theorem of calculus that told us that to evaluate this definite integral, we did not have to actually compute the limit of a sum as n goes to infinity. We could instead use antiderivatives. We would like to turn our approximation of the average of the function value into a definite integral to take advantage of this powerful calculation technique known as the fundamental theorem of calculus. We've already got a lot of what we need. Our formula so far for the average function value has the limit as n goes to infinity. It's got the sum as I goes from 1 to n of f of x sub I star. The one thing it's lacking that our formula for the area has is that delta x. Let's see how we can get that delta x in there. We're going to need some rectangles to do that. So let's put in some rectangles. I've divided the interval from a to b up into n rectangles. You can now see that I chose one x value from each rectangle to get my x sub I stars. I think this video is long enough, so let's pick up with this in the next video. I'll see you then.